I think we can wait for about one more minute before we start. Yeah,
Okay, sounds good. Just let me know then.
yeah, okay. Okay, I think we can start now. Hello everyone, welcome to Supporting Vietnam with the technical sharing. And I'm very happy to have Andre from Aki Blockchain Security with us to talk about Trident, the first Fuji framework design for Solana program. So, Andre, can you introduce a bit about yourself and then you can start your session?
Yes, for sure. So, yeah, welcome everyone. Thanks for the invitation. And of course, I will introduce myself. First of all, as you mentioned, I'm going to present the Trident, which is the first fuzzing framework for the Solana programs. Currently written using the Anchor framework, but we want to ship Trident to support also programs written using just the vanilla Solana. From my side, who am I? So my name is once again Andre. I'm an auditor at Eki or Aki. Sometimes I'm also a developer here, and yeah, my Twitter handle you can see on the screen. What we do as a security company, so the most important part, I guess, is or are the audits. So in Aki, we audit Solana and the EVM chains. Then we also do, as is also point of this presentation, we do tooling. So more precisely, we develop Wake, which is first, or not so, sorry, not first. It is fuzzing framework for the EVM chain, and we also do the Trident, which is a fuzzing framework for the Solana chain. And then, yeah, we also teach crypto. So in Prague, our CEO teaches on the university. He has a blockchain subject. And apart from that, we run School of Solana, Auditors Bootcamp. We had already 6 runs of the School of Solana. Auditors Bootcamp is more security oriented for already advanced developers. So yeah, check our website and you can register for upcoming runs. From our clients, so we work with one of the best clients from the both of the ecosystems. So you can see the Marinade, Wormhole, also Helio is pretty big client on our side. Then we received also some grants from Coinbase, Ethereum Foundation, and also from the Solana Foundation. We are also partner, educational partner of the Solana Foundation, and they also sponsor the Trident. So yeah, this is big thank you to the Solana Foundation. All right, and as I said, the Trident is first fuzzing framework for the Solana programs. But you may ask, what is fuzzing? It is kind of not that common word. So what that means? All right, so the fuzzing is an automatic technique that provides random, valid, or invalid or unexpected input data to your in this context to your program. But it is also pretty well known in the Web2 security. So it can be to the protocol, to some kind of software, to hardware, etc. And it helps to discover the unknown bugs and vulnerabilities. Why is it important? It is pretty simple. It is important because when you write your POC tests, most of the time, if the smart contract you just wrote contains some kind of math logic, you will most likely test it for the most common numbers such as 0, 1, 5, and etc. But with fuzzing, you basically can test the smart contract for the whole scale of the numbers. So if the mat function uses unsigned 64 bits long integer, then the fuzzing basically tests all of the possible values from this range of the unsigned 64 bits long integer. So that is also why we actually choose fuzzing, because we want to increase the test coverage as much as possible. As I said, the fuzzing is pretty common in the Web2 security. You can find a plethora of resources about Web2 security and fuzzing. I think recently when I was checking the resources, how many bugs were found in the Google, I think it was in the Chromium using the fuzzing, it was in thousands, not just the hundreds or tens, but in thousands. So you can see how many bugs you can find with the fuzzing, because it tests the edge cases. And what is also important, it can be also misused, because it can be used by both sides, so also by hackers to discover vulnerabilities and edge cases, edge values, and so on. As I already mentioned, it discovers unexpected values, edge cases. It is in most cases set it and leave it. So when you are done with writing your Solana program or smart contract, then you just set up the fuzzer and leave it run for several hours or even days, and then you can increase coverage and the confidence that it actually went through everything. It has also low maintenance because, as I said, you do not need to write a new POC test for each of the value from the range that it can or it uses, but it automatically generates the random data. So you do not need to write multiple POC tests, but you just need to specify the fastest template within the Trident, and the Trident automatically handles the randomization of the inputs. And yeah, it is easy to scale. You add new instruction to your smart contract, then it is easy to add the new instruction to the fastest. And also the second thing that you can do is completely recreate the fastest template and just copy the contents. But this is why it is easy to scale. It is possible to also be implemented in the GitHub pipelines. So this is definitely another level to the smart contract security. One of the results we have, so this was the motivation, because as I said, Wake is on the EVM side. Wake was or is also pretty famous, well-known, and successful in the discovering bugs and edge cases on the EVM side. So this is why we actually decided to proceed with the development of the Trident. So as you can see, Wake discovered multiple medium and high severity issues. So that is why we decided to develop the Trident. In the Trident perspective, we have already some highs, but they are not available currently publicly. So the table is not shown in here. All right, and then what actually is a Trident? I was talking about the fuzzing, I was talking about the template, but let's talk about the Trident in more details. So first things first, the Trident is a Rust-based CLI tool. What that means, it is similar to Anchor. So if you have your Anchor project, just within the root of the project, you can call Trident init. It will automatically build the Anchor project, take the IDL, and from the IDL, create the fastest template. We can also call it Rust frontend for well-established fuzzers. So in a simplified way, the Trident use under the hood AFL or the Honk Fuzz. You may know this because they are also utilized away from the crypto or blockchain space. So Trident just helps you to fill the fastest template and then run the AFL and the Honk Fuzz under the hood, which are responsible for generating the random data. So yeah, as I said, this is the next step. So Trident is used for creation of the fastest template, which is the front end. And in the brackets, it is called gray box in this case, because it is not completely black box. Black box would mean that you do not need to specify anything and just run the fuzzer on the smart contract. However, in this case, you need to fill some of the data in the fastest template. As you may know, there are PDAs or some instruction input data that might be more unique than other inputs. So you can customize these, or in some cases you are obligated to. All right. Yeah, I was talking about the field the template. PDAs, etc. are difficult to generate. Then you run the fuzz test, and what the AFL and the honk fuzz actually does under the hood, they are working pretty nice with the coverage. So we can call the Trident coverage guided fuzzer. That means the AFL generates some random data. These random data are used on the instruction inputs, and then the AFL knows how far in the smart contract it came. So that means it can remember, based on the coverage of the smart contract, how successful the random instruction data were. So it is not just silly creating random data, but in with some kind of good approach, it generates the random data semi-randomly, let's say. All right, now about quickly the fuzzing template. As I said, the fuzzing template is created from the IDL. So at the start, when the fuzzing template is created, basically the Trident scans the IDL, takes all of the available instructions, and these all available instructions are inserted into the fastest template. We will see this later in the hands-on example. The instructions consist of the instruction account. You can see this also in the code snippet on the right-hand side, and the instruction data. So in this case, the Trident took the instruction from the IDL, and the instruction consists of the author account, hello world account, which is PDA, and the system program, and the instruction data is just a simple input. Then these instructions are packed into the transactions, and then these transactions are executed in our Trident SVM, which is fast execution environment utilizing the ANSYS SVM. Transactions are then fast randomly, or you can decide what sequence or flow of the transactions you want to fuzz. So what that means, if you are already skilled developer in the Solana ecosystem, you may know that if your smart contract has, for example, 10 instructions, you expect that these instructions are going to be executed in some order. That means, firstly, some kind of initialization is going to be called, then some kind of buy, sell, upgrade, whatever, withdraw, and then at the end, some instruction that will close some of the accounts can be called. So you can specify this particular sequence of transactions that you would like to invoke. That means the Trident will not execute completely random sequences, but will start with your implemented flow. So that means with the initialization, then with some number of cells, buys, what you define, and then with the close instruction transaction. And yeah, the user's role here is to help to resolve some of the accounts. In most cases, these are only the PDAs or the instructions data. There are some niche cases where you want to upload, let's say, address to the Solana blockchain because you are working on fuzzer. So in this, fuzzer on a bridge. So in this case, you do not want to let the Trident to try completely random addresses to be uploaded to the Solana blockchain, but you want to specify some constant one. So this is how you can help basically the Trident to fuzz correctly. All right, random inputs. How are the inputs actually random? So the random data are generated by the, as I said, AFL or the HonkFuzz, which are underlying fuzzing engines. And then instructions are then created from this random data. What that means? It is really simple. You take the byte array, which was created or generated by the AFL or the HonkFuzz, and you try to deserialize this byte array into the instruction. If it's all right, then it will proceed with the execution of the instruction. If the data are not good for the instruction, then it will try different instruction, different data. Then the instructions consist of instruction data and instruction accounts. Instruction data are mostly, in most cases, really simple because these are primitive data types in most cases, unsigned integers, strings, byte arrays, and so on. If it's struct or basically custom data type or enum, it is also pretty simple because these custom data types then again contain some primitive data types. So in this case, creating instruction data is simple. What is not that simple is instruction accounts. And why is it not that simple? It is because addresses are 32 bytes long. So you cannot let the fuzzer to generate completely random account addresses, because it would lead in most cases to basically failing the transaction or unsuccessful execution. Because if you can do the math, 32 bytes is 256 bits long input, and I'm not sure if you can still see the screen. I just received a message from Jonathan.
I see screen. Yeah, the random input rồi.
Sorry, does it work?
Yeah, I still see your screen.
Okay, so I can continue. All right, so I was talking about the instruction accounts, and as we cannot let the AFL to generate completely random addresses, so instead of that, what we do is we actually let the fuzzer generate indexes to the storage. So what user do is user tells the Trident, this is the PDA, or these are the seeds. It automatically calculates the PDA and store it for later. So in the first occurrence, for example, in some initialization, you define the seeds. You tell the Trident that these are the seeds for the PDA, and it will automatically store it in the dedicated storage and use it for additional instructions. And yeah, as I said, fuzzer just generates indexes to the storage. So instead of the addresses, it generates the index. So sometimes it tries the correct address. Sometimes it does not try the correct address, but that is completely all right, because if your fuzz test is written correctly, it is part of the fuzzing to also test the smart contracts to be invoked also with different addresses than the correct one. All right, and now I would like to talk about some customization that is possible with the Trident. And the first thing, for example, is that Trident supports transactions with multiple instructions. That means in some cases you want to execute, or your smart contract contains logic with the flash loans. So you want to take the loan, do some stuff, and then repay the loan, so everything within one transaction. So this is possible to fuzz with the Trident. So you can create, as you can see in the code snippet, you will also see this in the hands-on example. You can create the transaction with multiple instructions. It is really simple. It is also possible to define transaction hooks. transaction hooks are basically methods that are automatically executed based on the desired behavior. We have currently pre-transaction hook, post-transaction hook, invariant check, and we have also error handler, but that is this one is not that often used. Pre-transaction hook is automatically executed before the transaction invocation. Post-transaction is automatically executed after the transaction invocation. So, for example, the transaction was executed and you want to, each time after the transaction is executed, you want to forward in time, for example, or you want to change the slot, or you want to change the epoch, or create some token or some different behavior. Same goes for the pre-transaction hook. And then the invariant check is used for the differential fuzzing. That means the invariant check has on its input a snapshot of all of the accounts that are used within the transaction before and after. That means that you can compare if the accounts were changed as expected. So that's basically the idea of the differential fuzzing. So you in the some of the fuzz test, you check that the behavior is same as within the smart contract. So that is another level of security and correctness of the smart contract. All right, and the last customization that I have specified here is the fuzzing flows. So as I was talking about the custom sequences that you can define. So I'm not sure if you can see the mouse cursor. All right, nope. All right, so from the code snippet at the start of the fuzz test, the initialization of the smart contract, just the smart contract, not any kind of instruction. The initialization of the smart contract deployment is performed. You can see that within the function called start, which is marked with the attribute init. And then after this function, there is another function called flow1. You can have multiple flows. And within these flows, you can specify your custom logic. Flows are executed in sequences. So if you have multiple flows, let's say the first flow is called flow 1, then the second one is called flow 2, and so on. So these are going to be executed in a sequence. We are currently exploring additional attributes. So for example, the flows can be executed in a random, they can be shuffled, ignored, and so on. And within the flow, you can see it is really easy to construct and execute the transaction. So you just take the transaction, you call build function on it with the fuzzer data. The fuzzer data in the code snippet is actually the random data that fuzzer created. Then there are some additional arguments such as clients and accounts, which is the account storage. And on the result of this build invocation, you just call the execute. And that is basically everything. Fuzzer will handle everything or the other stuff. And this will ensure that the initialize transaction is basically called within the flow number 1. All right, this was all from the introduction. I would like to have a quick hands-on example. So just let me check if everything works correctly. So everything is all right?
Yeah, but I think there are some problem with Twitter, so some people cannot see the stream. Okay, I'm fixing it, so you can just keep continue.
All right, so can I continue, right?
Yeah.
All right, so give me a second. I will reshare my screen. And what I want to share is this screen. Hopefully you can you see the source code?
Yeah, I can see your screen.
Okay. So yeah, I have very simple hello world Solana program here written using the Anchor framework. and the program actually consists of two instructions. The first one is called initialize, and then the second one is called update. Within the first one, it is pretty simple. We just take the input argument, which is unsigned 8 bits long integer, so 1 byte, and we assign it to the hello world account. We can have a look what hello world account stores, and this is just the 1 byte and the authority pub key. The authority is not that important within this example. That's the initialization. Then within the update, we do something similar, but we take the input and then we take the input and then we add it to the already existing input or already stored input within the hello world. So really simple. You maybe would think that this example is correct, but the arithmetic here can overflow and it can be considered as a security or a vulnerability. In this case, it won't actually overflow, but it will panic. But also this kind of vulnerability can be considered as denial of service, for example, in some cases. In this particular case, this is really simplified case, but yeah, in some more robust programs or smart contracts, this can be also taken as I said, denial of service. So I want to share the Fuzz test right now. So let me again reshare. And this time, let me share the window, not just the tab. Okay, you should see again the VS Code, right? Yes.
Yeah.
All right. So this is the folder that is created with the Trident. The folder is called Trident tests. And if you are just initializing the Trident within your workspace, you or the Trident will initialize the first Fuzz test as Fuzz0. The Fuzz test is split into the instructions, transactions, and then some additional files. Types are meant for some custom types that you would like to define. Test Fuzz is basically something like main file for normal Rust programs. And then we have Fuzz transactions where we actually store where we actually have defined the storage for the accounts. All right, so let's start with the instructions. So if we navigate to for example, the initialize fn.rs, we can see that this is basically the interface to the initialize instruction. You could see this in the slides. I have here the structure for the initialize instruction. Here are the instruction accounts. And here are the instruction data. In this case, only one field called input, and it is 1 byte long, basically. What we have here is that the author account is always going to be mutable for the initialize instruction. It is always going to be signer, and we specify the storage where the author address is going to be used. In this case, the storage is called author. Once again, I can navigate to the Fuzz transactions, and we can see that here is defined the structure with all of the storages. So it is pretty common that you do not fuzz the system program. So for example, what we can do, we can comment this out because we do not need the storage of the system program, but let me leave it here. Then for the second account in the initialize instruction is the hello world account where we actually store the input. In this case, we have something similar, but we do not have it specified as a signer. We just specified that what is the storage where the address is going to be stored and what are the seeds, because this account is or has actually the address as PDA. And then for the system program, this is completely all right to specify it as a constant. So we have specified here as a constant with the address equals and the system program account program address. All right. Same goes for the update function or update instruction. The interface is pretty the same. But as you can see, for example, we do not have seeds here for the Hello World account. And that is because it is ensured that the seeds are, or the PDA is created here in the initialize, for the initialize instruction, and the final PDA is inserted into the storage. So what we can do here in the update instruction, we can just specify the storage, and it will, in this case, it will take the address, not add the address, but it will take the address from the storage. Sometimes the address will be incorrect, but sometimes it will be correct. As you can see, we will be able to basically actually fuzz and find an issue. And then same goes for the author. So we just specify that, okay, Trident take the author from the author storage. And again, the system program can be constant. Let me delete these two functions. These are not important right now. And I was talking about the multi-instruction transaction execution. In this case, I do not have it specified in this fuzz test, but what I can do is to, let's say, copy, in this case, the instructions, rename the instructions, and what it would done is that the initialized transaction would actually call 3 initialized instructions within one transaction. As I said, it can be in some edge cases or not edge cases, because on Solana, instructions are pretty often bundled into the transactions, so this can be also pretty useful. All right, and now let's move to the test fuzz, to the res. So as you could see also in the slides, you can see the main function, which is basically the start. So we just initialize the Trident SVN client. This is not that important. What is more important is that we create new fuzz test. We specify that within the fuzz test, we want to use the Trident SVN client, and we start the fuzzing with the fuzz method. The fuzz method will firstly start or call this start function, which initializes and deploys the program. You can see we deploy it with the program ID and the entry point. The second thing that is executed after the start function is the flow. As I said, we can, for example, what we can do is we can copy the flow 1, rename it to flow 2, mark it as a flow, and the fuzz test would actually execute this initialized transaction, then this update transaction, and then again initialized transaction, and then update transaction. What might be important to mention is that for each of the transactions, even though if the transactions are the same, the random data are selected or created by the fuzzer, by the AFL, by the honk fuzz. That means this first initialized transaction wouldn't be executed with the same input data as this second one. All right, so let me remove this fuzz tool. So once again, what we are saying here is that fuzzer or Trident take the fuzzer data, which are random, which is random byte array. So take the random byte array, build initialize transaction from the byte array, and then execute it. And then same goes for the update. Now I would like to share you this. Hopefully you can see can you see the terminal?
No, I don't see it.
Okay, so I will reshare. Now you can see the terminal.
Yes, but can you zoom out a bit?
Sorry.
Can you make it bigger? That is. Can you hear me?
Do you want me to increase the size?
No. Okay. I can see it. Yeah.
Okay. So, and as we have specified the fuzz test, now we can do Trident fuzz run hfuzz, and Fuzz0. Fuzz0 is actually the name of the fastest. So as Trident firstly initialize the fastest with name Fuzz0. If you invoke Trident Fuzz_add, it will create Fuzz1, Fuzz2, and so on. So which fastest you would like to call, just use it here as the Fuzz target. Now I press enter. I will definitely have some warnings in here, but give it a second and you can see. It was pretty fast, all right, because this is really simple example. There are in this window, there are transaction outputs. And in the uppercase upper part, I'm not sure if you can see the cursor. Yes, you can see. In this upper part, there are some statistics from the fuzzing. So for example, number of iterations, you can see there the remaining time until the fuzzer will run. This can be specified in the separate file, which is called trident.tomo. You can find this in the documentation. I have specified that the fuzz test should run for 20 seconds. So you could see that it ran for 1 second and it already found something. How do I know that it already found something? You can see this on this line with the crashes. So it actually found 3 crashes, but it found just 1 unique because all of the 3 crashes were the same. So it only stored this one. And yeah, that's pretty everything important from this part. What is also important are the stats here. You can see the which of the transactions were invoked. So you can see this initialized transaction was invoked, the update transaction was invoked. You can see the total number of invocations, how many times it was successfully invoked, and how many times it was the transaction failed. In this case, for example, the initialize did not fail or failed 0 times. The update function failed 17 times, but never mind, it still managed to find something. All right, now we want to actually see what it found. So in that case, we can remove the run and call debug hfuzz with the same fuzz target, but in this case we need to specify the crash file. This is kind of tricky because the crash files are automatically saved by the AFL and the hongfuzz, so the path is not that simple. So what you need to specify is fuzzing folder, then hongfuzz, hfuzz workspace, number of name of the fuzz test, and then there are the crash files. The crash files always start with the big capital S. So in this case, seek_arpt and some stack trace. Press enter. What it actually does under the hood, it takes the fuzz test, and on the fuzz test it actually executes the crash file. All right, this is the crash file. So some of the stuff may be familiar to you. Let's start from the starting point. So firstly, there is the info, what instruction with what parameters what invoked. So firstly, the initialized transaction or instruction, in this case, because the initialized instruction is only the first transaction contained only 1 instruction. So in this case, only this initialized instruction was called. You can see the discriminator, which is not that important. In this case, also accounts are not that important, but the input data are important. Why? Because we store this 255 in the hello world account. Then some Solana logs for example, debugging, or some emit logs, messages, and so on. And then you can see that the second instruction was executed, and that was the update one. Once again, we can skip the discriminator, we can skip the accounts, but in this case, instruction data were invoked, or the instruction was invoked with the instruction data specified as 10. As you may probably know, the unsigned 8 bits long integers in Rust can be maximally 255. So that means if we take this number and add 10 to that, it will overflow. But you can miss this overflow as a developer. So Fuzzer will try basically all of these values for you. And as you can see, it can spot the mistakes, it can spot the overflows, and immediately panic and immediately store the crash file, which you can immediately debug. All right. Stop sharing. Let me come back to the slides. All right, this was basically everything from the hands-on example and the presentation, and I have slide for Q&A. So yeah, if you have any questions, feel free to ask.
Yes. To be honest, it's a bit new to us about Trident. Yeah. Okay. So we can use Trident with existing Ancon program, right? Can we?
So sorry, I cannot understand.
I mean, if I have a Ancon project and I can use Trident, right? I don't need to create a new one, but I can use with my current Ancon project.
Can you please write the question to the Telegram chat? I can read
Yeah.
it in the
Okay.
Telegram. Would it be possible?
Yeah.
Okay, thanks.
Yeah.
Sorry, but I cannot see the question.
It's on your comment. It's on the chat box. Can you see it on your right hand, on your right side of the screen? A comment.
Nope. I see private chat, but I do not see anything in there. But you can write it on the Telegram. We have
Yeah.
common channel.
Do any people have any question for Andrew? Feel free to send on your comment. Do you have any UK to apply Trident? For example, if I writing NFT program, I think a marketplace NFT program, can I use Trident to test the functions?
I'm so sorry, but I cannot understand you.
Okay, I will turn off my. Oh, can you hear me now?
Yes.
Yeah. I just wonder if I'm writing NFT marketplace program, and can I use your framework to test my program?
If you can use my friend, if you can just Trident for what was the concept, what was the theme of the program?
Yeah.
But what was the program about? Did I hear marketplace?
NFT marketplace.
NFT marketplace.
Yeah.
Yeah, you should be able to fuzz also NFT marketplace.
Yeah. Yeah, okay. I think there are no more questions right now. So yeah, I
All
think
right.
we are good. Mm,
All right. So yeah, in that case, thanks for the invitation. It was pleasure to have the presentation for the Super Team Vietnam. And yeah, if you want to use Trident, check the Trident, or sorry, the URL is use xyz, sorry. And then you will find a lot of additional information here, for example, documentation, and then yes, or you can reach to us on the Discord. Okay.
yeah. Okay. So yeah. Okay. I think we're good. Thank you everyone for joining us today. And if you have any question, feel free to contact Andrew or us on Twitter or on Telegram. Okay, a big thanks to Andrew for your time and your expertise. I'm very happy to see you in your future workshop with Super Team Vietnam. Yeah, and
Yeah.
thank you everyone. See you next week.
Thanks. Enjoy.
Yeah,
Bye.
okay, bye. See you.